Okay. Despite its name, this paper is really as much about cognitive theory viewed through the lens of music as the other way around. One of the two major historical approaches to cognitive theory has been that of symbolic computationalism, which sees the mind as being made up of discrete modules fit for distinct functions. This allows us to produce a functional map of the brain. In contrast, connectionism models cognition as a connected network that can be tuned to produce certain outputs for a given set of inputs. The main distinction here is that there is no symbol manipulation, just gradients of data going from input to output and vice versa. Although these views have traditionally been seen as oppositional, some of the more recent successful advances in artificial intelligence research have come about by merging the two. There is another approach, though, modeled after a steam engine governor and named after a ship steersman, Kubernetes, whence our modern term cybernetics. In this paradigm, the central connecting element is neither obscured, as in the hidden layer of a neural network, nor fixed, as an encapsulated symbolic module would be. Music theory can be a useful tool for investigating this kind of model precisely because music exists dynamically in the gaps between the notes. Which means that the goal of music theory is to investigate connections between objects in symbolically tractable ways without disrupting the flow that is intrinsic to the subject matter. To help visualize this concept, consider this classic impossible figure. In order to get a sense of what we are seeing, we can break the object into discrete, sensible parts, which can be encoded in some language, and then these encodings can be individually analyzed. And the result recombined to produce theories or closures about the object under investigation. The encoding language used here is the noise profile of datasets, following from the observation that one particular such profile, pink noise, is ubiquitous in phenomena ranging from neural firing rates to word frequencies and indeed music, an observation known as Zipf's law. This ubiquity makes the pink noise profile a suitable candidate for a common language of description between various phenomena. This is because noise profiles can be used to find boundaries between regions of data. In the example shown here, we have two unequal regions of white noise. Where the change between region occurs, the overall profile will shift to red, while locally an intermediate pink noise profile will be observed. The noise profiles are defined by the slope of the logarithms of how often each note occurs, plotted against the logarithms of the rank of those events, so that the most common event is rank 1. Pink noise is defined as a slope with a value near -1. It may be because explanations can be thought of as descriptions of phenomena in terms of boundaries between unequal yet locally stable regions that Zipf's law is observed in the first place, since pink noise optimizes information density. Here we can see a noise profile of Bach's first duetto from his Klavierübung number 4. The middle two profiles show each individual voice, while the outer ones shows two different ways of combining the profiles, either by averaging their values or by adding the data together. Even at this very basic level, it is already possible to see important motives and section boundaries as shown here. However, when one starts delving into them, it quickly becomes apparent that there's no single way to read the results that will reliably automate analysis. In this figure, for example, we can see 12 convolution windows. The bottom one, the top one looks at every 2 successive notes, while the bottom one combines a whole bar. Rather than trying to work out which view is the correct one, we can collect all of this information into a single figure that gives us an overview. I call this process semantic injection by combination, and it allows us to see complex data structures at a glance. Here I've plotted some very simple vectors to show how these figures are constructed. The triangle figures that are produced in this way show structures in 3 ways. The starting point of a section runs from left to right, the end point runs diagonally across, while the length of a window of analysis scans from top to bottom. So in the bottom left corner, we find a cell that corresponds to the whole length of the word, while the top left shows the first unit by itself and the top right, the very last unit by itself. A second form of semantic injection can be done by selectively only counting some elements, such as considering the notes that occur in each key. This allows us to run different key profiles where each line represents a different modal slice of the complete data set. These approaches can then be combined as shown here, with the triangle representing the noise signatures of the key profiles at all convolution lengths. The rectangle in the bottom right here has a convolution size of 24, which is represented by this line of pixels. We can then plot some major boundaries found through any of the existing musical analysis tools onto such a chart to evaluate how effectively it has managed to reflect independent interpretations. The corpus used here is the Pacinium genre, which extends through a wide range of historical periods. Despite the fact that the nature of this sort of music is to overlap and obscure boundaries, some examples work really neatly, while others can be less clear. Telemann uses material in his canons very cleverly to fulfill multiple functions at different times. This can make it difficult to draw sharp, conclusive boundaries, something that these charts reflect quite adequately. However, especially where key changes are dramatic, as in the third canon of this sonata, boundaries are still clearly visible and sensible. This is not so in the case of Rieger, where the boundaries are not only vague, but also difficult to align with theme entries and other paradigmatic cues. It is almost as if the structure is more of an impression than a sharp, in-focus picture, even if it is possible to find post-hoc justifications for certain readings. Bach's four duets offer a suitable balance between these extremes, with some examples offering abundantly clear boundaries, while others are less precise, although never quite as much as in the Rieger examples. In some cases, though, the boundaries could hardly be more apparent, bearing in mind the three boundary types, start, end, and length. One of the most interesting works in this genre is the first duetto. It is at once highly structured and very fluid, so it is worth a deeper look. There are a number of different ways in which data can be added and subtracted from one another to highlight or obscure certain features. In general, though, this does not change the underlying fixedness of the musical object under investigation, but can improve the focus. In this example, we can see the ratio of average values to combined values, a relationship that is often quite effective. For some pieces, though, such as in this first duet we looked at by Romano, the change does very little to improve the quality of the analysis, and may in fact have a bit of a negative effect. But in others, such as this Rieger example we looked at, the improvement can be quite dramatic, showing that the apparent lack of clarity seen in the original analysis was perhaps more of a function of the choice of analysis than an intrinsic property of the work itself. In general, it's remarkable just how robust the results are in general. This figure is a post-produced version of the combined data of that first Bach duetto, put through a random dithering process. Major structural points are still clearly visible, and it may even reveal some novel analytical insights that we might not otherwise have read. Still, while it is useful to optimize boundaries by mathematical manipulation, the approach comes dangerously close to the backpropagation techniques of neural networks, with all the drawbacks that that entails. The major advantage of this approach, though, is that we can tune the semantic injection by bringing independent analytical techniques together. Here we can see this approach in action, looking at just the opening bar of the first Bach duetto. The top row of figures shows just the simple noise profile of the pitch classes, with weightings corresponding to ideas of tonality and beat hierarchies. The remainder are weightings of the raw noise profile, weighted by the inter-onset interval of 12 different recordings. So, to make more sense of these figures, we can subtract the performed values from the ones calculated with theoretical weightings. Subtracting from the raw values gives an indication of where each performer deviates from the straight 30 seconds condition. see that the agogic emphasis was less than predicted by our beats model. So this is the performance minus the beats. So the performance didn't quite use agogic accents quite as much to emphasize the beat as I suspected with this model. There is in some of these models a very distinct line there, which is related to the metrical division of 4 beats, 4 subbeats. The difference from the key modifier shows that none of the performers emphasized the highest note of the segment with an agogic accent, as might have been expected due to it being the tonic. The differences between the performance in the final weighting is quite small and quite close to directly opposite to the raw difference, perhaps highlighting the fact that Bach has managed to avoid placing strongly tonal notes on every strong metrical point. This is why Bruin and Hewitt show stronger deviations when they slow down at the start of the second half, with the beat and the tonal points are maximally offset. We could now adjust this weighting profiles to reflect more local information, instead of just assigning an overall key of E major or E minor to this whole segment. In this way, we can compare our intuitions and theoretical constructs directly with constructs realized by performers, composers, and listeners, as measured by any given method, whether it be physical gestures, direct brain measurements, loudness profiles, in fact, virtually any parameter we can practically measure.
As our next speaker sets up, we have time for one question.
Thank you for your talk. Perhaps you explained it and I missed it, but when you were plotting the triangular plots, it wasn't clear to me how you were establishing those segmental boundaries.
Those were just like formal analysis, just looking at it and seeing where I thought was a good place to put a boundary. A lot of these have very overlapping boundaries, and it's the composer, like very often Telemann he'll use things like that. So there isn't always an obvious musical place where you can say, that's where the boundary is, because he deliberately obscures it. So I put where I thought was a good answer over what the formula basically said.
Oh, I see.
Yeah.
Okay. So those lines drawn were your interpretations and your...
Exactly. Yes. One has to compare it to some interpretation from something else. Yes. Otherwise, one can sort of tune it to produce anything. Yeah.